Hello and welcome to our webinar, The Value of Prototyping Prior to Production, how the learnings from prototyping improve production. My name is Mark and I'll be your moderator today. Our featured speaker is Stanley Zavatski, a Senior Technical Account Manager here at Xcentric Mold and Engineering. Stanley holds a bachelor's degree in plastics engineering technology from Penn State University, has been in the manufacturing realm for 8 years, and has substantial experience in production injection molding. This presentation is expected to last approximately 50 minutes and is being recorded. A link to the recording will be sent out within 48 hours. There will be a Q&A session at the end of the presentation. Use the questions field on your screen to submit your questions. We encourage you to follow Xcentric Mold and Engineering on LinkedIn so that you can stay up to date on our latest blog topics and webinar schedules. Also, follow Stanley, whose contact information is on the screen right now. I now turn over the webinar to Stanley.
Thanks, Mark. All right, let's jump into this. First off, thank you everyone for joining. But like Mark said, about a 50-minute presentation. We'll go through it, have some questions in between, and then we'll have questions at the end. So let's start out. Why to choose prototyping? One of the big things initially is to prove out design on a cheaper tool. There's nothing worse than thinking you have the correct design, go to production on a full production tool, and then you realize that some of the parts aren't right. The costs that you have to incur changing a production tool rather than a prototype tool are going to be much higher. So you get to kind of do a lot of that stuff initially on these cheaper tools, prove out what you want, and it's a direct correlation to what your production tool is going to be. Next is a quick turnaround time on parts, especially for functional testing, but for marketing. And again, these are pretty much equivalent, if not the same part of what your production tooling is going to be. So you can get these pieces sometimes as little as 5 days from us on these pieces. Next, it's easy to create production parts while you're waiting on the longer lead times for production tooling. Production tooling, typically, you see an 8 to 12 week lead time on them, can be much higher depending on the complexity of the part. So in between, you can really use this not only as a prototype tool, but as kind of that bridge tool moving into production as well. And then you get to really evaluate these parts in the real world and not in a simulation. So a lot of parts will go through mold flow, will go through some sort of FEA, and a lot of these testing. And we found that while doing these simulations are correct, you can pretty much spend the same exact cost that you would on a simulation on actually getting a full prototype tool and having those pieces. Then the next thing is leveraging those lessons you've learned through making the tool, through running the parts. Everything you learn through that, you can directly correlate it to a production tool. You can transfer a lot of the process settings, everything, and you know what you've done in the past is going to work once you move it into production. So kind of the types of prototyping and when you want to use them. So we start out with 3D printing. Typically, you're looking at 1 to 10 pieces. You're just doing a feasibility of the design to make sure that everything's good. You really want something to hold in your hands to make sure what you've designed in CAD, what's on that drawing is really what you're looking for. Kind of fit some of those pieces together. Some of the concerns you get with 3D printing can be the surface finish isn't going to match up, the material isn't going to be exactly what you have on your parts. And really these are for much lower volume because the cost when you try to go much higher on these is going to be too high compared to some of these other options. The next one's cast urethane. This one, again, this is for lower volume, kind of when you want more pieces more close to what you're going to get with an injection molding. You're going to be in that 10 to 100 range. These parts have a surface finish, so they're going to be very comparable, if not the same, to injection molding. They're going to be great for marketing to get these pieces, kind of have them because they're going to look great. And then you're going to be for functional testing. These are going to be much stronger than what you're going to get from 3D printing. So you can do some more of that testing on these when you're quite not ready to move into a full prototype injection molding. And then once you get into that, we're looking prototyping up to 2,500 pieces and then low to mid volume range, production, bridge tooling, kind of that 25,000 range, 25, 50,000 range. And this is going to be, again, a direct correlation to what you're going to get on your full production tool. You can do everything that you would do on a normal production tool: complex features, inserts, overmolding. You're going to have the exact material that you're using on that. And you're also going to look at some of the parameters that are going to be changing once you get into production, like what the shrinkage of the mold is going to be, some warp, if you're having sink in some areas, if you're having splay on some of the parts. It's really nice to get that kind of sense of what it's going to be like before you move on to production. So I'm going to stop here and start with the first question. So this question is, what is your awareness level of all the parts and molding parameters evaluated during injection molding prototyping? All right, I still see the answers coming in, so I'm going to give it 10 more seconds and then I'll close it out. All right. So it seems like a lot of people here have at least some understanding of what these are and what you're looking for. And the next slide, we're going to start diving deeper into this. We're going to look at some of the part features. We're going to start really looking more at what we're looking at and what we're evaluating. So some of the part features we review in prototyping. This is going to be not only in the molding aspect of it, but it's going to be prior to that. A lot of the DFM work that we're going to work with you directly on, trying to get your parts to the state where have a really good part for manufacturing. So the first one's undercuts. What we do is typically a lot of hand loads on undercuts. So instead of the full automatic slides that we're going to move whenever the mold opens and closes, the way we do it is we will create a feature that when the mold opens, an operator can pull that out, pull these pieces apart. It really allows you to get every undercut that you designed. You're able to see if it works, if it's going to be sticking, if it's going to lead to any issues ahead of time. And we can simulate all that in our prototype tool. Now, there's two different ways to look at it: internal and external undercuts. Both of these we're going to do with hand loads in-house. But when you get into the production tool, the hand loads, or the automatic slides, excuse me, start to add size onto the mold. So really evaluating if you need all these undercuts on it, and if this mold, once you move into a 4, 6, 18 cavity tool, if it's really going to cause problems in mold size, if you're going to have to go up to a larger molding machine. A lot of that stuff can be evaluated beforehand in prototyping, so that way once you get into production, you kind of know what you need and what it's going to look like. The next is draft. This seems to be an afterthought on a lot of parts, but it actually plays a huge role into the tool life. One of the issues when a part doesn't have draft, the plastic is injected in, it starts to cool around the core side of the mold. And as it's doing that, it's kind of shrinking in and sucking to that core. If you don't have draft on it, when we go to eject it, you start running into issues where the part's going to be sticking on the core. And then that's going to lead to cosmetic issues, but also it's going to start to wear the tool away. Every single time that it's moving and closing, it's going to be pulling on that surface. Another thing is you're going to get cosmetic defects where you're going to see those maybe scratch marks or little marks on the part. And once we add that draft to it, it allows that part to slide off much easier. It eliminates the potential risk of breaking anything in the process. excuse me, but it also helps in automation as well, because once you get into a fully automated tool in production, now you have robots coming in to grab these pieces, whether it be with suction or fingers to grab them. And if they're sticking, then you run into the issue where the robot can't grab the part. The mold then closes on that part, it alarms out, and you have to hopefully have no damage to the tool, but then you have to start pulling pieces off of it. So all these little things that we look at in part design really help with that. The next one's wall thickness of it. Wall thickness really helps with moldability of the part. When you have an uneven wall thickness in the part, you get these very thick sections and thin sections. You run into issues where you can fill the thick section, but then you don't fill the thin section because the mold is freezing the plastic before it gets all the way to the end. But also there's other things that get into this when we look at warp on the part, because differences in shrinkage will cause the plastic part to move around, but you also get sinks and voids. So internally you'll have voids where plastic doesn't fill out because of those differences in shrinkage. And you can also potentially get sinks on the surface of the part. Another big thing with wall thickness is cost reduction. When you have a very large, thick piece, it's in prototyping, it's not a huge deal because you're not making that many pieces. But once you go into production, if you're running tens of thousands, hundreds of thousands, millions of pieces, every little bit that you save on mold, on material will help in the long run. Next are quarters and radiuses. So when we're looking at a lot of parts that come to a sharp point on the end, that creates a lot of stress right there at that point. And that stress will lead into the part, which could lead to further problems in production, but it could also lead into failures in the final part at the end with parts snapping, breaking. Another big thing, it creates more of that uniform wall thickness, like I was talking about, all the features it had on there. The uniform wall thickness just really helps out the part, not only through manufacturing, but in the final application. It tends to be more cosmetically pleasing as well, having nice rounded edges instead of sharp edges onto that. And then shrinkage. Again, when you have a sharp edge on a tool and it starts to shrink around that, it then suctions against that, where when you have these sweeping corners and stuff, it allows it to push off of it much easier than when you have a straight 90-degree angle. Next is ribs. Ribs really add strength to a part. I like to use the example, if you look at a plastic shelf, very large piece, multiple feet in each diameter, and you look underneath of that, you have these very long, skinny ribs underneath of it to add that strength that you need for all the things. And it helps with the cost reduction as well, because you're taking what would be a giant piece of plastic, making it a very uniform wall thickness and adding these ribs underneath of it. So you're saving a ton of money by adding ribs instead of just making the part thicker, beefier type thing. And again, it helps with the eliminating voids and sinks in the part, because with those thick sections you run into some of those defects where you have voids on the inside, or you have sinks that are just not cosmetically pleasing, especially if you want these pieces to have a customer facing side to them. Bosses kind of go hand in hand with ribs. It is a rib in a sense, but it's a deviation of that. So bosses are great for locating in assemblies. If you have two pieces that are coming together, you have a boss on one end with a hole, the other end you have it with a kind of a pin, and then you can locate that and bring the assemblies together. And then you have screw holes in assemblies. Again, similar to the way that you're using it for locating those screw holes. Instead of having a large slab of plastic, you now have a smaller hole that you can screw into. And it provides cost reduction the same as all the rest of them, because you're eliminating the use of more plastic on it. And it adds strength the same way that ribs do. They're very similar, almost hand in hand on the applications that you use them for. And it's really nice when you can use that instead of larger sections of plastic. And then last, surface finish. Surface finish affects the life of the tool. So you can have anything as abrasive as a very rough surface, and you can have it to where it's almost optically clear. When you get into some of those higher surface finishes, becomes more difficult to maintain the tool, because any little thing that touches it, scratches it, then you start to see that directly onto the part. So really knowing what application you need and what surface finish is going to be the most robust for your process is going to be huge. And it's going to help on the final part, because you're reviewing all this stuff ahead of time, so that way you don't have to make these changes again once you get into production. And then for secondary operations, if you have these very shiny surfaces on some of them, they tend to scratch more easy. Sometimes a robot's not able to pick them up because it can't get the suction or can't get the finger marks onto it. So all of these play into, and it's all things that we think about and work through ahead of time, so we can get that piece into prototyping and then get that piece onto production. All right, so we kind of looked at some of the features of the part itself. Now we're going to start looking at the features in the mold, the way the mold's designed, and we'll get into some of the automation that goes along hand in hand with this. So some of the gate types, these are just a few. There are pretty much any gate that you can think of out there that can be used for different applications. So the first one, a direct sprue gate. Like it says, it's directly into the part. It fills a part rapidly without losing a maximum pressure drop to get the whole way through. The one downside with these sometimes is you are getting a large surface blemish. You are getting some not a defect, but just something that's not as pleasing to the eye. And next is the tab gate. So a tab gate, an edge gate, a fan gate, they're all within the family. A tab gate has a very specific use to it compared to some of the other ones. It's very good for thin parts. The way it reduces shear of the plastic through the gate. So you see this a lot more on polycarbonate, acrylic, really clear pieces. That way you're not seeing any shear of the plastic when it goes into the piece. Next is edge gate. This is kind of the catch-all be-all of gating for plastic molds. It is the one that we use most, and we can do all of them, but edge gate is typically the one that we use for most applications. It's a very generic gate that can do everything. It's not great at anything, but can do everything that you need it to do. And then we look at fan gate. A fan gate is really used for fast filling of large parts. It kind of fans out as the name is, and you can fill a lot of plastic into a part once you start getting into some of those larger pieces. And it creates more of a uniform flow through the piece as well. So some of the issues we talk about, warpage, shrinkage, those different things, the dimensional stability, this kind of helps in aiding on some of those, especially on those larger pieces. So now we look at some of the automatic trimming gates. The gates above are all gates that you need an operator to take off the piece after it's been molded. Once you get more into production, you start looking at some more of these automatic gates, because you are trying to automate the process. You're trying to use as least amount of operators as possible to get your final piece out the door. So the first one's a tunnel gate. Chisel gate, submarine, there's a bunch of different names to it. This one's really great for getting inside of a piece. If you want to not have a gate on the outside of the piece, any show of it, this one can be used to get into an internal feature and gate directly into that. Another nice thing, once this mold opens, it trims the gate directly off. So you don't need an operator sitting there grabbing each one of the pieces and ripping the gate. The next one's a pin gate. These are typically used on larger parts when you need multiple injection locations. It can be It's very small, so it can be used in a lot of different places, and it can create more of a uniform fill on the piece. Because once you start filling these larger pieces, if you have a large injection time, then you start getting differences in shrinkage on it. You get different cooling throughout the pieces, which can lead to warping. So you use pin gates on these larger pieces to kind of do that. And then the next two, hot tip and valve gate, they're very similar to one another. Being one just has a actual valve that shuts off where the other one doesn't. So hot tips are typically used on very high volume applications where you're just pumping parts out over and over, because as it says, it never truly freezes off. So you get a bit of string on it. So it's good for if the part is just going to run. The next one's valve gate. Very similar to the hot tip, but it has a shutoff pin. So these are used in a lot of higher application volumes where you want to be able to shut that off, have the part fully cool, have the part fully set before you're ejecting it out. So that's the variation between those. Next is ejection. There's multiple different types of it, a couple I've listed below. Pins are probably the most used in industry on everything. They are very good at ejecting the part, can be used in a bunch of different areas, can be large, can be small. And then we have blades. Blades are really used for getting areas that you can't get a pin in, whether the diameter is too small. Think of like a large skinny wall where you're worried it's going to be sticking to the mold or you're not going to get it fully out. You can put a long blade in there to kind of help get that piece out along with pins. The next is a stripper plate. This is typically used on more cylindrical pieces where it's holding around the outside of the surface. The mold will open and then we'll pop the third plate to pop it off. This is in production is great because once the mold opens, you can have the robot come in, grab onto those pieces, and then the stripper plate will push the mold forward, pieces will come off, a mold will close, and continue the cycle onward. All right, so now we're going to move into another question, and I'm going to launch it now. So what is your awareness level of all the components that can be used in production injection molding? All right, we're going to have 10 more seconds and I'll shut it off. All right. So it seems like everyone's at least has some familiarity with the different things. I'm going to show a few on the next slide. Some of the ones that I like, some of the things that we do internally that then will be automated fully in the next step of it. All right. So the first one, slides. So I talked about it earlier and talked about how we do hand loads. So hand load again is an operator is physically pulling the piece out with metal around it to form some of those undercuts or features that can't be done in a traditional open and closed type mold. Once you get into production, you don't want that operator standing there. You don't want added cost into that final piece. So you start adding slides. So this really, when the mold opens, things start to pull apart that allow the piece to have those undercuts automatically removed, and then a robot to come in and pull the parts, or the parts to drop down onto a conveyor belt underneath. The next one's a collapsible core. So again, we do it with a hand load, have the operator pull it all out. But in a full production mode, you have a pin that will pull down and actually collapse the metal core. These are used on, think bottle caps, any internal undercuts that you can't really get to any other way that would be in a cylindrical type form. You use that collapsible core to pull that apart and get those pieces off. Another one I think is really cool. I mean, it's very difficult. You can see the picture below is the unscrewing threads. So the way we do it was with the hand load, the part comes out, and we actually have an operator physically twist that insert, put it back in the mold to run the next piece. When moving into production, especially on some of these higher volume applications, you just want to automate this. And there's a lot of detail that goes into it, and it creates a very, very large mold because of all those gears that need to go into place, the way that it opens and closes. So it's things that can be added onto the mold in production that we're simulating in prototyping. And the next one, it's kind of two-shot overmolding. I'll clump them into one category. So the way we do it is we shoot the first piece we call the substrate out of the first material, typically a harder plastic at first. We will mold all of those at first, and then we will switch the mold over, bring the second mold in. We will grab that piece, stick it in, and then overmold that piece onto it. Typically a softer plastic, sometimes just a different colored plastic, whatever the application may be. But the way it works more in production is you get into a two-shot machine where the mold has both of the molds that we created in one, and then the machine has two injection units to handle this. Typically, it can be done either by a mold spinning and then having a second injection location, whether it be vertically coming down in or from the side into it. So you'll shoot that first piece, the mold will spin or mold will move into the second location, and it just creates a continuous process of making that piece. Now we've kind of reviewed some of the features of the part, what we looked at internally, and now we're going to look at some of the pieces that are added on after the fact to automate your final design. So robotics. You have a sprue picker is the most basic form of robotics. It comes in, it grabs the runner system, pulls the piece out and drops it either on a conveyor or into a bin, whatever it may be. And then you get into a little more advanced, a 3-axis robot. With these, you then build a plate onto the face of it to go into the cavity and grab each one of those pieces. So it can be little suction cups that'll go in and grab it, or actual little fingers that'll go grab each piece individually. And this is great on some of those higher applications, or when you're moving it, that piece over into an automated packaging cell, or if it's going into any of these other applications where you need something, a task to be handled and don't want an operator handling that task. So some of these secondary operations could be pad printing. The way we do pad printing in-house is we shoot all the pieces, grab them, and then print them after the fact. But as you can see in the picture, the robot will come and drop the pieces onto the slide, which will then bring it down in and print each one of these pieces and slide the pieces off into a final bin. The next one's ultrasonic. So again, we mold the pieces and then do the ultrasonic second. But another value in the prototyping aspect is we can prove out that the design is correct, that it is able to be welded prior to it, and kind of do all that on a much smaller scale. So that way, once you move into the application where you want to handle more of that on a production level, you're like, okay, we've done this, it works. Now, how do we automate this so we can move it into full production? And then we have labeling. There's tons and tons of different ways to label, whether it be outside, in the mold. This picture, for example, is, think of the actual label going into the mold, closing, plastic shooting around it, and then popping the part out. And it's an automated process like that. Some of the applications are after the fact. Think of bottles where you shoot the bottle, fill it, and then put the label on top of it after that. So there's a bunch of different labeling. And all of these can be added on to the process once you're in production. And then packaging. A slew of different ways to pack your parts. Can be bulk packing where you're just counting 1,000 in a bag. It could be the robot coming and picking and putting so many parts in a tray and then moving that tray down the line. There's many different options on how to do all this. All right, we are going to move into another question. So this one is, which of the following process parameters affect part performance and piece price? Select all that apply. All right, we'll give it about 10 more seconds and then I'll shut it off. All right. So it looks like everyone got it right. We'll move into the next slide and I'll give a little more details on the results of this. So processing parameters to review and prototyping. So like I said, it's all of them. Really every aspect that you can look at, every detail that you can get out of something is going to be valuable to moving it forward to the next stage and producing the part that you want in the long run. So injection pressure. You're always going to have variations in injection pressure. That's just the way the process is. What is great is limiting that variation and bringing that process to where it's controllable variation and you know what is going to make good pieces and bad pieces. For injection pressure, maxing out the machine is huge. So when we're prototyping, we're making sure that we're keeping our injection pressure at a reasonable amount, because if not, then you're going to run into issues when you're trying to go to production and you want to build a larger mold. If you're maxing it out on a one cavity small mold, you're definitely going to run into those issues moving into a higher cavitation. And a lot of the things that we can do with this is start changing runner sizes or looking at the piece to make sure that everything's good. And we can make a lot of those changes in prototyping, prove out kind of everything you want to do, and then take all of that with you over to production. Injection time. So injection time is going to play into shrinkage of the part. You have a very long injection time. You're going to have that difference in temperature of the plastic inside of it, and it's going to be different in shrinkage, whether it's at the end of fill, beginning of fill, and that can lead to warping of the part and can lead to other defects. You want to create a repeatable process. Everyone is always going to say that repeatable process on everything. So bringing in an injection time that's repeatable on every single one of them, then you know that the part coming out is going to be the correct piece. And then cooling on the end of it, kind of this, to go with that shrinkage, is cooling. You don't want to heat large variable on any of these parameters. So bringing that whole process in, bringing cooling down to a smaller thing will create a better part. Hold pressure. This really is for packing the part out at the end. This is going to reduce your shrinkage, having a full pack part, and create a dimensional stable piece. It's going to have a very uniform part through the whole process, and this is kind of one of the final stages to make sure that you're getting everything into the part that you need. Cooling time. This is going to affect the overall cycle time of the part, which in prototyping isn't as large as it is in production. When you're running hundreds of thousands, millions of pieces, every little second tenth of a second will make your piece price cheaper. The cosmetics of the piece. If your part's still a little too hot, when you're popping it out, you could risk having an ejector pin push through and make like a little blemish, or there's a slew of different issues of having a piece too hot coming out that will affect your final part, including the dimensions of the part. Having a uniform cooling time on every part is going to make sure that you're going to have the same dimensions of that part over and over. So now we're going to look at a couple part examples, mold examples that we've done in the past, and how we've worked through them. So the first piece is an overmolded part that you can see all the ejector pins and is subgated. So you can see the level of detail each one of these pins is going into, having a specific application that it needs to be. So this piece is a overmold. Shoot the first piece, which is the green, and then move that over to mold the yellow piece, which is the overmolded. For this particular application, the part is subgated, so that way the customer-facing side doesn't have any blemishes on it. Everything is underneath, more of where the assembly. This mold too looks like a 2-cavity, but it's actually what we call a left-right mold. So for handles, we create both pieces in one mold and then can assemble it after the fact on that. The next piece, it's a medical part with sliders, a stripper plate, single gated, and then what's really important about this piece is typically when you have a large cylinder piece with a hole running through it, you don't want to use a single gate on a side, because what will happen is you will start injecting, and that pin that is in there kind of free standing will start to deflect a little bit, and this will affect the center diameter of the part. You'll run out of your concentricity through the whole of it will start to be off a little bit, and you'll have issues where the hole will veer off towards the end. What we were able to do with this piece is actually have that pin that runs up the whole way through be held on the bottom, but also on the top. So we're holding that pin in both locations, so that way when we're injecting with a single gate, we're not getting that deflection of the pin on the inside, and we were able to have a repeatable process and create that concentricity the whole way through the piece, part after part. And with this mold, we have 2 slides coming in to form it, and then a single pin that goes up into it. And then the pink piece is actually the stripper plate that then helps eject the part into its final application. The next piece is a cap with internal threads and a locking feature. So again, these are all things that we can do internally that will be used on a final production. So you can see all the little pieces that go into forming those threads on the internal portion. And then we are able to pull that core out and pull it out, and you have the full function of the threads and all the features. Just doing it with a hand load instead of doing this with a unscrewing mold or collapsible core. Everything is simulated ahead of time, so you know. And with this specific application, we made a 2-cavity mold, but what we did was we shot the first side, proved out the process that we wanted, and then came back and open the second side, and everything that we figured out on the first side moved to the second side. And we were allowed to use this for a bridge tool, helping them get to a full production tool later on. All right, so we kind of reviewed all the different features, whether it be part design early, some features in the mold, automation after the mold, and some of the processing parameters. That these are all the things that we're working with and going through and prototyping, and all the efforts to move into production. And one of the things I do want to point out is that we actually do some production in-house. Some of the benefits, we have the knowledge of the product because of the prototyping effort. So there's no transfer of data to anyone from machine to machine. We've done all this work. We know how the part runs, and we can help with some of these lower production volumes. Another big thing is sometimes we can use that same mold that we use in prototype to actually do production. It's not applicable in all cases, but I would say a large number of them, we can use that prototyping mold. And the way we can do that is we offer a lifetime warranty on those molds. So as long as the part runs at our facility and an order is placed within 2 years, then we can offer that lifetime warranty and run those pieces. So what I like to say is we do bridge or low volume production, typically under 50,000, depending on the cases and depending on the piece, but we are able to do that. Another benefit is just a lower mold cost. Making out of aluminum instead of steel is lower to begin with. And if we can use that prototyping tool that we had as the production tool, you're saving money because you already spent the money ahead of time, and you can move on to the next. So I have one final question to ask. It's going to go live. Would you like an engineer to contact you to discuss rapid injection molding prototyping for a current or upcoming project? All right, I'll give you 10 more seconds and I'll shut it down. All right. So it seems like some people do. I will make sure that we talk with the internal team and have someone reach out to you guys and help you out. All right, now just some of the capabilities we have. Injection molding, like I said, we can have parts to you in as little as 5 days, and that is from a PO being submitted, mold being cut, pieces on your door in as little as 5 days after that. Part runs, I said 50,000. We have it listed as 25,000. Really, it's a case by case type thing. So it depends on what the piece is. We can do up to 1.5 pound shot size, so some pretty large pieces. We can do single cavity, multi-cavity, tons of different options. And then we have 55 ton to 300 ton electric presses, so we can do a variety of sizes, parts up to 2 feet by 2 feet by 5 inches in depth. CNC machining as well, parts in as little as 5 days. Part runs anywhere from 1 to 100 to 1,000. Really, we're open to all cases. We can hold pretty high tolerances, plus or minus 5,000. Do a variety of different materials, metals, plastics, different surface finishes. We can do ion plating. We can do a slew of different things. And then rapid prototyping. We have a slew of different rapid prototyping options, whether they be 3D printing like our SLA, SLS, multi-jet, or some of those higher volume ones that you want to do, the cast urethane as well.
All right, well, thanks, Stanley. Appreciate the insight on how those lessons learned in prototyping apply to the production situation. Folks, we're going to open it up now to audience questions. Again, please use the questions field on your screen to submit your questions. All right, we've got a couple of them that have come in while you were talking. The first one is, why is wall thickness uniformity so important in part design?
Yeah, so that's a big one. That's probably one of the fundamental rules that we learn throughout schooling and just plastics. Having that uniform wall throughout the piece really creates a sound piece, dimensionally stable piece in the long run, and is going to be great for manufacturing and great for your final cause of not having issues with parts in the field.
Next question. Yeah, we hear this one a lot. Why are hand loads cheaper than automatic slides?
Yeah, so hand loads are, since it's much more of a operator function, and you don't have to add all those extra elements of designing a mold that's going to open and move all these slides out of the place. It's just a cheaper way to get your final piece out. There's just not as much machining time, engineering time that goes into it. You're still going to get the piece you want out of it. It's just not as difficult to make.
All right. Next question. Somebody has asked, do you have a material list? And we do. So I will, when we send out the link to the recording, in that email, I'll include a link to our material list so you can see everything that we have in-house. Another question, Stanley, can we have a say in what gate we want to use on our molds?
Yeah, absolutely. I gave a few options of gates. There's more options as well online, and that can be a discussion factor when we're going through the DFM work, and we can talk with our internal design team as well and make pretty much any gate that you want to use.
Okay. Next question. What is the maximum in glass fill that we run?
That's a good question, and I don't know the answer to that one. I've seen 60% on a few parts I've worked on. I'm not sure if we've had higher than that or not.
All right. Well, we'll do a little research to find out what is the highest we've used, and be sure to include that also in the follow-up email. Another question. What is the optimal prototyping approach when you're dealing with a part formed of an assembly of 8+ plastic subparts?
Yeah, so that's really important initially on the design aspect, to make sure that you're doing your stacking of your tolerances, your stacking of your dimensions, to make sure that if you do have variability in the part sizes, that the piece is going to meet kind of go together properly. So I would say initially it starts with design to make sure that you're having parameters where that part's still going to fit into, and then once it gets into prototyping, making sure that we're making those parts within that tolerance that is called out so you can put that full assembly together.
All right, next question. Do you run, I think this is, do you run glass-filled, it says Riton. Do you run glass-filled Riton?
Yes, we do.
Okay. All right. I don't see any other questions coming in right now, Stanley, and we're at about the 50-minute mark. So we'll go ahead and close out. Thank you, everyone, for joining us today. As I said, we will be sending a link out to the recording of this webinar within about 48 hours. We'll also be sure to include a link to our material list and a follow-up as far as what our glass fill maximum is. If you have any questions about the topic presented here today, please email us at info@xcentricmold.com. Have a great day, everybody.